Hi, this is Dr. B.J. Swaraprasad, Professor of Civil Engineering, G. Pullareddy Engineering College, Autonomous, Kurnool. In this video, I am going to explain the design of solid apron for an hydraulic structure. As part of the course, Design and Drawing of Hydraulic Structures, DDHS, there are several structures, hydraulic structures, namely, already I mentioned the entire syllabus is covered in various modules. The first module is Introduction of DDHS and module 2 is on surplus weir. This is one of the major hydraulic structure which is required for irrigation. That's why it is also known as irrigation structure. In the earlier videos, I explained about the various design components of surplus weir. In the present module or present video, we have to discuss about the design of solid apron. It is a part of design of surplus weir and also some of the drawing features of this structure surplus weir. So as mentioned earlier, the syllabus, once again, if you go through the syllabus, introduction, estimation of flood discharge, selection of type of work, regarding the weir, length of the surplus weir, crest width, base width, etc. And then followed by some of the protective works like abutments, wing walls, returns. So these are all discussed earlier. Now in this present video, we are going to discuss about design of solid apron. So and also revetment and bed pitching as a miscellaneous work, some specifications, etc. Now coming to solid apron. Generally, these aprons, solid aprons in the form of impervious floor are required for all the hydraulic structures, especially on the downstream side of the structure. For example, in case of a dam or a barrage or even for weir, on the downstream side of the structure, it is necessary to provide such a solid apron in the form of impervious floor to protect the structure against the soil erosion. That is the main purpose of the providing this solid apron. Now coming to this present problem, so we are discussing this design with reference to a numerical problem. So for which how to design the solid apron, so which includes some of the numerical calculations also. The first of all, upstream side apron. Generally, no aprons are required on the upstream side of the weir, most of the cases. However, it is desirable to provide a puddle apron, puddle clay apron as shown in this figure. Here we can observe this is the upstream side of this weir wall. So this portion has to be filled with puddle clay filling, so which will act as a solid apron. It is also sometimes provided with a nominal rough stone apron of 30 cm thick packed well on puddle clay apron. Even after filling this clay in this portion, the top layer of this portion has to be filled with rough stones of 30 cm thick. That's why it is called a temporary or nominal apron. Now coming to the downstream apron, this is most important and also necessary. It is necessary to provide a solid apron, that is impervious floor, on the downstream side of any hydraulic structure to prevent the failure of the structure due to uplift pressure, that is called undermining. One of the failures of the structures, hydraulic structures, are like piping failure, uplift pressure failure, like that. So this is the major cause of failure of the structure. That's why against this failure, we need to provide the solid apron as the protective measure. In the present case, since the ground level, coming to the numerical problem under consideration, and it has given in the problem statement, since the ground level is falling down to 10 meters, the level of existing ground is plus 10 meters over a distance of about 6 meters. So therefore, existing ground level near the structure is 11 meters, it has given, and for a distance of 6 meters on the downstream side, the ground level is 10 meters. That means there is a difference of elevation difference of 1 meter over a distance of 6 meters. Hence, it is desirable to provide a stepped apron as shown in figure. See here, if it is a solid masonry wall, that is a weir wall. On the downstream side of the weir wall, we are going to provide the solid apron like this, stepped apron. The reason is existing ground level near the structure is 11 meters, and from the structure downstream for a distance of 6 meters, the ground level is 10 meters. That means there is a drastic difference in elevation ground level by 1 meter over a distance of 6 meters only. That's why it is better to provide the stepped apron. So this figure shows the position of the solid apron on the downstream side of the weir wall with all usual notations. Now coming to design of the solid apron. So generally the design of solid apron is common in nature. The procedure is similar for all the structures. Whatever the structure may be, the procedure, the standard procedure. Let me explain the design procedure of the solid apron, which is essential for any hydraulic structure. So there are two important components for the design of apron. They are the length and thickness. Generally the design components are length of the apron, that means how length we have to provide the apron on the downstream side, and what about the thickness of the apron to be provided or required. So first of all, let us consider the length of the apron. The length of the apron may be fixed on the basis of piping failure. As I mentioned earlier, so many causes of failures are there. One of the failures is piping failure. Piping means undermining, and the second one is the uplift pressure failure. Due to uplift pressure developed, the structure may fail. Similarly, due to piping also the structure may fail. Piping means the progressively backward erosion of soil. That you might have known the definition of that piping. So therefore, this length of the apron is purely with respect to the piping failure. By considering the safety of the apron against piping, we are going to fix the length. This is the basic concept behind to fix the length of the apron. Safety against piping means the necessary condition, the requirement for safety against piping is given like this. So this is already we might have studied in previous topics. The hydraulic gradient, you are all aware about the hydraulic gradient, H by L, should be less than or equal to 1 by C. There are several methods for the design of impervious floor. So Blick's creep theory, Lane's weighted average theory, and coast loss theory, etc. So whatever the theory we followed, this is the common procedure. So hydraulic gradient should be given by H by L should less than or equal to 1 by C, in which H is the total head causing the seepage, L, capital L is the total creep length, and capital C is the creep coefficient or coefficient of creep. So these are the three parameters involved in this condition. By considering this safety condition, we are going to fix the length of the apron. The aprons may be designed for a hydraulic gradient of 1 in 5, which is safe enough to prevent undermining of the structure. Generally, this hydraulic gradient, how to adopt the value of this hydraulic gradient, in which H by L is equal to 1 by C. C is the creep coefficient. So generally this creep coefficient as per Blick's theory is in between 5 to 17 like that. So therefore depends on so many factors like nature of this soil, nature of the ground, etc. So we have to adopt the suitable value of the C, or in other words hydraulic gradient as 1 in 5 or 1 in 7 like that. So in the present case, we are assuming the hydraulic gradient as 1 in 5, which is safe enough for prevention of undermining of the structure. So in the present problem, when the water level in the tank is up to the dam stone, that is up to the top of the shutter, which is given as 12.75 meters with no water on the downstream side. So here we should observe carefully the relative levels, water surface levels as well as the existing ground level or the floor level, etc. So therefore on the upstream side, we are stored the water in the tank up to plus 12 meters. It has given in the problem. So in the case of necessary, we can also store water up to plus 12.75. That means 0.75 meter additional storage can also be allowed. So by providing the shutters, with dam stones. Therefore, this 12.75 meter level is the top of the shutter level or top of the dam stone level, which is incidentally the maximum water level in the present case. And also on the downstream side, we are assuming that there is no water, there is no tailwater on the downstream side. That means the level to be considered as existing ground level, which is given as plus 10 meters. Therefore, the total seepage head available in the present case to case it may vary. In the present case, the total seepage head or total available head for seepage is given as 12.75 minus 10, which is equal to 2.75 meter. We can clearly observe, see here, so this level is plus 10 meters, this 12 meter is the crest level of the weir wall, plus 12.75 is the top of the shutter or top of the dam stone. So from this 12.75 to this 10 meters. So the total head available. Why? Because we can store water in the tank up to plus 12.75 meter. That is the maximum water level. Whereas on the downstream side, the existing ground level is plus 10 meters. Therefore, this 12.75 minus 10 is equal to 2.75 in the present case. That is called total seepage head available. Now, if the safe hydraulic gradient is assumed to be 1 in 5, the total creep length required. That's a simple formula. So as H by L is equal to 1 by C, we consider the equation or necessary condition. So accordingly, the total creep length is given by L is equal to C into H. So where L is the creep length, C is the creep coefficient, H is the total head available. Accordingly, 5 into 2.75, it is equal to 13.75 meters. I hope it is clear. So as we assumed that safe hydraulic gradient as 1 in 5 and available head is 2.75, therefore the total creep length is 5 times the 2.75, which is equal to 13.75 meters. This is total creep length, not length of the apron. However, as shown in figure, the total length of the apron required is, now coming to the apron length. So again we can refer this figure. The total creep length means from, as shown in this figure, from A to B, B to C, C to D, and D to E, E to F. So this is the path traced by the seepage water. Seepage water will move like this, in this direction, so in contact with the structure. So therefore, as shown in this figure, A to C, we can easily evaluate, we can easily abstract this value as it is 11 meters. The bottom of the foundation concrete is 9 meters, 2 meters in this vertical direction, and foundation concrete width is 3 meters, 2 plus 3, like that. So this is called total creep length, which already we calculated the total creep length as 13.75 meters. So in which, out of which, what would be the total length of the apron? Our intention is to determine this total length of the apron only. So from the total creep length. So accordingly, if you see here, 13.75 meter is the total creep length, not the length of the apron. So as shown in figure, the total length of the apron required is the 13.75 minus creep length from A to D and E to F. See here, A to D and E to F. So these vertical component of this creep path traced by the seepage, and also up to this D horizontal component, horizontal length, similarly from E to F. So accordingly, if you subtract these known values from the 13.75, you will get the total length of the apron. Say for example, you see here, this is 2 meters, this is 3 meters, 2 plus 3, 5, here 9 to 10, 1 meter vertical direction, so 6 meters. So out of 13.75, this is 6 meters, if you subtract, you will get 7.75 meter is the length of the apron required. It is very clear that the total creep length is different and the length of the apron is different. So total creep length inclusive of this length of the apron. Apron is in horizontal floor. So length of the horizontal floor required is 7.75. Or in other words, if you provide this much length of the solid apron on the downstream side of the structure, downstream side of the solid weir wall, we can protect the structure against the piping, right? So therefore, provide 8 meters, make it as round figure, 7.75 to be considered as 8 meters as the total length of the apron. See here. This 8-meter length is, as already we decided to provide this apron in the form of a stepped apron. So it is as the ground level is steep, the ground slope is very steep. Over a 6-meter length, it is having 1 meter elevation difference. That's why it is better to provide the stepped apron. So accordingly, this total 8-meter length to be provided in 2 steps with 3-meter length of the first step and 5-meter length of the second step as shown in figure. There is no hard and fast rule for dividing this total length into 2 steps like that. That depends on the existing situation and practice only. So in the present case, we are divided the total length of the 8-meter length of the solid apron into 2 parts, like 3 meter is as the first step and 5 meter as the second step. That is regarding the total length of the apron. So as a conclusion, so in the present case, we are going to provide 8-meter length of the solid apron. That 8 is also again 3 plus 5, 3 meter one step and 5 meter second step. Now coming to the thickness of the apron. This is the second important design parameter of a solid apron. So the thickness of the apron is determined by the consideration of safety of the apron against uplift pressure failure. So as already I mentioned, so these are the two major causes of failures of the structure. Accordingly, we are designing the structure. So the first length is the safety against piping. With reference to that, we fixed the length. Now the thickness has to be fixed with reference to the safety of the apron against the uplift pressure. You are all aware this seepage water will exert certain pressure which is acting vertically upward. So that is called, it is uplift pressure. The necessary condition for this safety against uplift pressure, a simple reason. So uplift pressure is acting vertically upward. So to nullify or to balance this uplift pressure, we need to provide sufficient thickness of the apron. So therefore, the self-weight of the floor, self-weight of the apron itself resists this uplift pressure. Accordingly, the necessary condition is uplift pressure should be less than or equal to weight of the floor. So this is the necessary condition. So accordingly, we have to fix the thickness. Again, the procedure is very simple. So we can consider this condition mathematical expression like this. So for example, if you consider unit area of the apron, say for example 1 square meter unit area. So what is the uplift pressure on that area acting vertically upward? What is the weight of the floor acting which is vertically downward? So these are equal and opposite. So simply we are equating these two forces. One is uplift pressure force, second one is the weight of the floor. Both are forces, so to be equal. So equal and opposite in direction, that's all. In a simple manner, with reference to specific weight or weight density, we can calculate the weight or force. So gamma W into H is equal to gamma into T. So you observe carefully, the uplift pressure is given by gamma W into H, where H is the uplift pressure head. So I think you are all aware about the pressure and pressure head. Pressure is the intensity of pressure. Pressure head is the height of the liquid column which exerts that much pressure. So therefore gamma W into H, if you consider gamma W is the specific weight or weight density which is given in Newton per meter cube, whereas H is in meters. So therefore the units for this term gamma W into H is so and so Newton per meter square. So that's why we are considering per unit area of the apron. Per unit area, this is the weight or uplift pressure force acting vertically upward. Similarly, coming to the weight, self weight of the floor, same, gamma is the specific weight or weight density of the floor material, and T is the thickness of the floor. So here also we'll get the same units. So gamma in Newton per meter cube, T thickness in meters, you will get Newton per square meter, Newton per meter square. So therefore, for compatibility, units will be same for both the cases. See here, what are the terms involved in this condition? It is very clear that gamma W is the specific weight of water, you are all aware, which is 9.81 kilonewton per meter cube or 9810 Newton per meter cube. Similarly, gamma is the specific weight of the floor material. So therefore, we can convert, or we can consider this gamma in terms of gamma W with reference to G, where G is the specific gravity of the floor material. Since it is convenient to express in terms of specific gravity, that is the relative density, always it is better to represent the specific weight of any material in terms of its specific gravity and specific weight of water. As you are all aware, you are all known that gamma W value, so that's why it can be converted into in terms of specific weight of water. And H is residual seepage head or uplift pressure head. This is a very important parameter. Always we should remember while designing any solid apron, especially the thickness of the apron, the H is the uplift pressure head. Uplift pressure head, which is also known as residual seepage head. Later I will explain what is the residual seepage head, how to consider that residual seepage head. There is only the parameter which is essential for fixing the thickness of the floor. So accordingly, by simplifying this equation, this condition, we will get the thickness of the floor T is equal to small h by capital G. It is a very simple equation or simple expression to fix or to determine the thickness of the floor. Small t thickness is equal to h by G. All the terms we know. T thickness in meters, h is the residual seepage head or uplift pressure head. Units are meters only, and G is the specific gravity. Therefore, thickness will get thickness in meters. Right. Coming to that is the general procedure to fix to determine the thickness of the floor. So T is equal to small h by G. You remember that simple formula. Always we are going to use that formula wherever it is required to determine the thickness of the floor. Now in the present case, the maximum uplift on the apron floor, that is on the bottom of the apron, felt immediately above the point D in this figure. As shown in this figure, let us consider again a typical surplus weir cross section and its foundation, and on the downstream side this is solid apron. Now we are going to discuss this solid apron, its thickness, right? So generally the uplift pressure up to this, it is the solid structure, so the seepage water will seeps like this in this direction, percolate, and here immediately above the D the maximum uplift pressure will exert, right? So this is one of the important point or salient point regarding this structure, the point where the maximum uplift experiences immediately on the downstream of the structure, so above the D. Suppose if it is our floor, bottom of the floor, immediately above this point D, here the uplift pressure will be maximum. Now, as part of the design, let us assume certain thickness. As usual, design means we have to assume first, and then we should check that assumed thickness is safe or not. Accordingly, in the present case also, assuming a thickness of 80 centimeters, 0.8 meter for the first step of this apron. Therefore, the bottom level of the apron, as per this assumption, here the existing ground level is 11 meters. Suppose if you provide the solid apron with its top equal to 11 meters level, from which 0.8 meter thickness if you consider, the bottom of the floor level is 11 minus 0.8, 10.2. You observe carefully, 11 minus 0.8. 0.8 is the assumed thickness. So therefore 11 minus 0.8 is 10.2 is the bottom level of the assumed apron. So therefore, up to here we need to calculate the total creep length. See here, the creep length from D to bottom of the apron. D up to D we know it is a known distance, 2 meter plus 3 meter, 5 meters we know as per the design. So from D to this point, bottom of the floor, this distance is 1.2 meter. As it is 10.2 and it is 9, this difference is 1.2. Is it clear? So therefore, the total creep length up to the point above D is given as 2 plus 3 plus 1.2, which is equal to 6.2 meters. I hope it is clear. Once again, you observe the total creep length up to the point under consideration. Here the point under consideration is bottom of the floor immediately above the D. So therefore, we are required the distance from A to this point. The reason is the water will seeps in this particular path. So therefore, the total creep length up to the point under consideration is given as 2 plus 3 plus 1.2, 6.2 meters. You can see in this figure also the detailed explanation. So this is the cross section of the weir wall with the foundation and followed by solid apron. First step of solid apron with a 0.8 meter thickness. The relative levels are, this is 11 meters. Here also it is 11 meters existing ground, and for a distance it is 10 meters. That's why you have shown like this. So now let us assume the water level on the upstream side is up to maximum water level, that is up to 12.75 meters. There is no tail water on the downstream side, right? That is up to 10 meters. So therefore the total head available is 2.75. As already I explained, 12.75 minus 10 is equal to 2.75. This is the total seepage head available. It is also very clear. As usual, as discussed earlier, the thickness of the floor is given by T is equal to H by G, where G is the specific gravity of the floor material and small h, important parameter, that is residual seepage head. How to obtain this residual seepage head? Wherever we want to fix the thickness or wherever we want to determine the thickness, at that section or at that point, we need to determine the residual seepage head. That is nothing but uplift pressure head. So residual seepage head is nothing but uplift pressure head. So therefore, this residual seepage head or remaining head is given by total head minus loss of head. A simple logic. Total head minus loss of head will give the remaining head, that is called residual head, which is equal to uplift pressure head. Here in the present case, the point under consideration is the bottom of the floor above the D as shown in figure. As already mentioned, this is our point under consideration. Bottom of the floor above the D, this is the point under consideration. So therefore, here we are going to consider or calculate the small h, that is residual seepage head. Capital H 2.75 already known. Loss of head to be determined. Once if you know this loss of head, by subtracting this HL from total head H, you will get the small h value. That much procedure we have to follow. See here, these are the numerical calculations. So with the assumed safe hydraulic gradient of 1 in 5, that is assumed earlier, loss of head up to the point is total creep length up to that point divided by 5. H by L is equal to 1 by 5. Always you should keep in mind the hydraulic gradient H by L, either at any point or at the end of the structure, we can calculate. End of the structure, it is called exit gradient. Intermediate anywhere, we can consider the same ratio, so H by L. Here H by L is equal to 1 in 5, 1 by 5. Accordingly, loss of head H is equal to total creep length L by 5. So total creep length up to the point is 6.2 divided by 5, which is equal to 1.24 meters. Therefore, this residual seepage head is equal to total head minus loss of head. Total head is 2.75 as given in the problem. 1.24 is the loss of head. Just now we calculated like this. So therefore, this difference is 1.51 meters. This is the important data required for calculating or for fixing the thickness of the floor. And also, another assumption, if the material of the solid apron is assumed to be masonry, let the specific gravity of the masonry G as 2.25. This you should remember. Everyone should remember the specific gravity of certain materials, standard materials like concrete, masonry, water, etc. You are all aware the specific gravity of water is 1, the specific gravity of concrete is nearly 2.4. Similarly, the specific gravity of masonry is 2.25. This value you should remember. So therefore, the thickness of the apron required is T is equal to H by G, where H is 1.51 divided by 2.25, which is equal to 0.67 meters. So like that, we can calculate or we can determine the thickness of the apron required. However, in general, for any design, we are going to consider certain factor of safety. Here also, with certain factor of safety, it is better to provide the 20% extra as the thickness of the floor. After, if it is the calculated value, in the present case, the calculated value is 0.67. That is required thickness. However, we are providing 20% extra as 1.2 into 0.67, 0.805 meters. This is the thickness to be provided. So hence our assumed, that's why earlier we assumed approximately 0.8 meters at the thickness of the floor. Our assumed thickness is enough, safe, so we can provide the same, that is 80 centimeter thickness of the apron as the first step. This is the detailed procedure, step-by-step procedure to determine the thickness of the solid apron. So as in the present case, we are proposing two steps. The first step is 3 meter length, that is having 0.8 meter thick. Similarly, for the second step of apron also, the same procedure has to be adopted. Accordingly, we have to determine the thickness of the apron. Here the only difference is the creep length. So you can see, you can observe the first step of length 3 meters. We already see here the first step thickness 0.8 meter we determined. So that should be continued up to 3 meters. And the second step is here. Its thickness is not necessarily this much. As length increases, creep length increases, obviously the uplift pressure will decrease. Accordingly, the thickness can also be reduced. Proportionately, we can reduce the thickness of the floor. That is the reason. So therefore, suppose in the next step, this is our point under consideration, the starting point of this second step. So, or in other words, at the end of the first step. So therefore, if it is our point under consideration, the total creep length up to this point we have to calculate. Earlier, the total creep length up to point D, above D, we calculated. Now we have to add this length as 3 meters. That's all. If we add 3 more meters to the previous length, we will get the total creep length up to this point, right? So therefore, you see, this is only the change. Loss of head up to the point at the end of the first step of 3 meter length is given by 6.2 plus 3. 3 meter is the length of the first step. Therefore, 1.84 meters is the loss of head. You can also observe loss of head in this figure. Sorry, here. So here creep length is residual head is more than this. So accordingly, here also the total residual seepage head we can calculate. Whereas the loss of head will be more. Here loss of head is this much. As the distance increases, the loss of head increases. So here this loss of head is more, which is given as 1.84 meter. You can clearly observe the difference. In the previous case, loss of head is 1.24 meters, whereas in the second case, the loss of head is 1.84 meters. As usual, remaining procedure will be same. Residual seepage head here is H minus HL. The total head is remains same, 2.75 meters minus 1.84, which is equal to 0.91 meters. Accordingly, the thickness of the apron required is T is equal to H by G, which is equal to 0.91 by 2.25 meters. So therefore, it is around 0.4 meters. Here also with the 20% extra for factor of safety, so we will get its thickness as 0.48 meters. Therefore, provide 0.5 meter, that is half meter thick solid apron as the second step. So you can clearly observe this these two. The first step of 0.8 meter, second step of 0.5 meter. Obviously, the thickness can be reduced. For economical point of view, we are providing the stepped apron on different lengths and different thicknesses, etc. These are all meant for economy only. Okay, this is about design of solid apron, both length and thickness. I hope it is clear. To fix or to determine the length of the apron required and thickness of the apron required. Now coming to certain specifications. So this is also required before going to draw the structure, drawing features. So you need to learn about certain specifications. In between design and drawing, these are required. So what are the specifications? Just a couple of minutes I will try to explain. So foundations. What are the specifications required? Obviously, as already I mentioned, the foundation concrete, unless otherwise specified, it should be a minimum of 2 feet, that is 0.6 meter thick, right? For nominal mix, concrete mix, as 1:4:8 concrete or mud concrete, etc. Some lean mix is enough to provide the solid, foundation concrete, right? That is the specification regarding the foundation concrete. Similarly, body wall and retaining walls. Generally, all the walls, if you observe in this present design, weir wall, abutments, wing walls, return walls, etc. These are all of either masonry or concrete. Most of the cases, all these walls are made with masonry only, for which certain specifications again you have to consider. Masonry, coarse durable masonry with cement mortar CM 1:6, like that we have to maintain. Similarly, dam stones. So dam stones purpose, to provide the shutters, we need to provide the dam stones throughout the length of the solid weir wall. So therefore, for the dam stones, either may be precast stones or stone masonry, cut stones. Those stones can be provided as dam stones. Similarly, solid apron and apron retaining walls, as shown in the previous figure. Solid apron and apron retaining walls are this. This is the solid apron. This is apron retaining wall. This is also apron retaining. At the end of each apron, each step of the apron, we have to provide such type of retaining walls for the prevention of soil erosion. The purpose is to prevent the soil erosion. And high coefficient cap. At the top of the weir, it is required to provide a cap. High coefficient cap, here itself we have to provide. Even though it is the masonry wall, at the top we need to provide with the concrete, that is solid concrete with rich mix like 1:2:4 or 1:1.5:3. The rich proportion concrete we have to provide as the high coefficient cap, right? And talus and connecting revetment. These talus and connecting revetments also, as part of protective works, additional safety. They may provide additional safety of the structure. So most of the existing structures you can observe these talus and connecting revetments, etc., as a stone masonry or a stone pitching, right? That we can observe in the drawing. Right, coming to the drawing items, these are the major items to be provided. A scale, as already I explained, everybody knows about scale. What is scale? Like 1:100 scale means, 100 units of the structure may be represented as 1 unit on the drawing. That is why it is called scale of 1:100. Now, these 4 major features you have to draw for any structure, not only for this surplus weir, any hydraulic structure, you are required to draw all these features. Plan, as mentioned earlier, plan as the top view. It should be half plan at the top and half plan at foundation, longitudinal section, longitudinal elevation, and also cross sections. We can see here. See here, just I will explain this drawing in brief. So this is the drawing of a surplus weir which we designed now. So after completion of the completed design of the structure, now we have to observe this drawing and the features of the drawing. So this is called plan. Half plan at the top, half plan at the foundation. As mentioned earlier, it is not possible to show all the details in a single drawing sheet. So always it is better to represent 50% at the top and 50% at the bottom, that is foundation level. So like this we can demarcate the plan like this. Left hand side of this drawing represent plan at the top. That means all the dimensions mentioned here are to be mentioned or representing the top dimensions at top. Similarly, half plan at foundation means all these dimensions are representing the dimensions at the floor level or ground level. So that's why it is called half plan at ground level or foundation level. Like this we have to draw the plan with a 1:100 scale or 1:50 scale. And this is longitudinal section. So if you observe, or if you stand here and if you observe the structure, it looks like this. That's why it is called longitudinal section. Along the length it appears. That's why it is called longitudinal section. Similarly, longitudinal elevation also. I think you are all aware about the sectional view and elevation. Elevation means in the vertical plane, side view, either front view or rear view, etc. all are shown in the elevation. So that means in the vertical plane we can observe all these things. See here the height of the weir wall, above which the dam stones, and by the side of which abutment, etc. These are all in elevation, that is vertical plane you can see. Similarly, certain wherever it is required, we have to represent the cross sections like this. All the cross sections are trapezoidal in shape. as this is the most common shape of the structure, trapezium. So for stability point of view, that's why all the walls, including weir wall, abutment, return walls, etc., all are of trapezoidal shape. The corresponding shapes are given here wherever it is required. And finally, section across the weir. This right hand side, if you observe, suppose if it is the weir wall, section across the weir. You see, observe carefully, this is the weir wall as we decided. Across the weir means, suppose if you see here from this direction, you can see all these features. Weir wall followed by one side, that is upstream side, and downstream side solid apron, etc. So these are all representing the section across the weir. So all the dimensions in the sense all the elevations and distances, most of the cases relative positions, relative elevations, as well as all the details should be provided. So ultimately, as part of the drawing of any hydraulic structure represent all these four important features: plan, longitudinal section, longitudinal elevation, and certain cross sections, in which we have to represent as maximum as possible the information, that is the data, like relative levels, relative positions in terms of RLs, and also the dimensions of the all the components, the top width, the bottom width, height, batter, splay, etc. All the dimensions as maximum as possible we have to mention. That would be the complete drawing of the structure. So I hope it is very clear. The design and drawing of hydraulic structure, this is the title of the course, in which one of the major structure is surplus weir. The purpose of the weir we know, how to design the weir, what are the various components of the design, weir, and lastly the drawing of the surplus weir. So this is the complete content of the design and drawing of surplus weir. Thank you.